All right, here's a calculation practice for us. We have a 76 kilogram hockey player moving at 6.7 meters per second. They collide with a 59.0 kilogram hockey player moving at 4.5 meters per second in the opposite direction. So here's the trick to these problems. This is the opposite direction. So this 6.7 meters per second, you better make positive, and then this one you better make negative, okay? Or vice versa, it doesn't matter, but you cannot make these two numbers the same value, okay? One has to be positive, one has to be negative when you're doing this, okay? After the collision, the 76 kilogram player slows down to 2.09 meters per second, while the 59 kilogram player has reverse direction, is now moving at 1.43 meters per second, okay? So a lot of these problems are organizing your information because we have lots of numbers, we have different masses in here, we have 4 different velocities in here. So I would definitely write this out. What's the initial velocity? What's the final velocity of the first person, of the second person? Make sure you have your negatives right, your positives right, because of things that are opposites. So you have that all this stuff together, okay? And then solve it, all right? So here's our questions. What type of collision was this, all right? So after collision, one is slowing down to this, the other one is moving this. They have 2 different velocities. If they have 2 different velocities, they're not stuck together, okay? So we already know that it can't be perfectly inelastic because they did not stick together. So it's either elastic, meaning this is a hypothetical problem we gave you, or it's an inelastic collision. So we know that already. So we want to go from that. Now, we know it's not perfectly inelastic. Okay, we've already explained why we know that. If it's inelastic, solve for the energy change. If it's elastic, explain why it's not a real-world scenario. Okay, so let's find the energy change, and then that will then allow us to determine if it's elastic or not. All right, so pause the video, try to solve it, and we'll come back with a solution. Okay, so here we go. So first of all, we know it's inelastic because there is an energy change and they didn't stick together. All right. Now we don't know for sure there's an energy change yet, but we're going to see that here in a minute. All right. So here's our work. We know our change of kinetic energy is 1/2 the mass 1, velocity 1, final, mass of object 2, velocity 2, final, squared, minus, it's your final minus your initial. Okay, so this is our setup. Now we plug all of our numbers in. Okay. So I made hockey player that's 76 1. So he was moving at 2.09 meters per second at the end. Hockey player 2 that was 59 kilograms was moving at 1.43 at the end. They were moving the same direction at the end, so they had the same sign here. Minus the original, it was 6.7 squared. This hockey player was moving the opposite direction, which is 4.5 meters per second squared, okay? So a nice thing is that negative sign that you put in here, we're going to square it. So if you miss it in this scenario, at least it would correct itself anyway because you're squaring it. So a negative squared is still positive. We end up getting this many joules of each player. So we add these up, subtract these away, and we get this minus this, and we get a negative 2,077 joules, okay? It should be a negative number, right? We should always be losing kinetic energy. So we have a negative 2,077 joules, so we have lost that many joules of energy, which means we have an inelastic collision. They did not stick together, so it's not perfectly inelastic, okay? That's one example of our practice. We will have more for you to do through homework and in-class stuff, okay? Thank you, guys. That is the unit.